Our last topic for this unit is power. And power is probably the most intuitive of all of our concepts once you understand its definition. Power is the rate of work getting done. So if you are getting more work done, you are more powerful. If you're getting less work done, you're less powerful. And again, that's compared by a rate. So that means that the average power can be calculated as work divided by time. And since we know the relationship between work and energy is that work is equal to the change in energy, then we can also say that the power could be measured by the energy transformed over time. And so this gives us two really easy ways to talk about and conceptualize and calculate power. So that means that if we were going to compare something to, say, the power of a horse, then it would be the amount of work that that horse could do over time. If we were going to talk about the power of a car, then we would talk about the car's ability to change chemical energy into mechanical energy over time. So these are two different concepts because it's how the work is getting done or how the energy is being transformed. Now, of course, a horse is also transforming its chemical energy from its food sources into mechanical energy for its ability to apply a force over a distance. But when we are curious about the power of a horse, we're really curious about how much force can that horse apply over that displacement of an object and how much time. So we're actually really just considering how much work can that horse do, and if it's powerful, what is the rate in which it can do that work. Whereas a car, we're interested in the power of the engine, and so we measure everything by our fossil fuel, which costs us money. So we want to say, well, what's the power of that car? How quickly can it transform its chemical energy into mechanical energy over time, and how much? So power has a unit. It's joules per second. All right, so it's the work or the energy over time, so joules over seconds, which is given its very own unit of a watt. A 1 watt is equal to 1 joule per second. You've probably heard of wattage before when we've talked about light bulbs or heaters or anything getting used in your house. Light bulbs and heaters change electrical energy into light and heat, which is thermal energy, over time. So that means that your house uses energy, and the rate at which it uses that energy is the power that your home requires. There's a few non-SI units for power. One of them is the foot-pound per second, and that's British. So it's how many feet and how many pounds of force in how much time. So foot-pounds would be the British unit for power. And then another one is horsepower. How much horsepower? And yes, that is based off of the average power output of a horse. And so to bring that unit into light, we could say that 1 horsepower is equal to 550 foot-pounds per second. So that's how much work a horse could do, 550 foot-pounds every single second. And the easy conversion for that is that 1 horsepower also equals 746 watts. So you can convert back and forth there. And obviously, while two different people might be able to do the same amount of work, some people are more powerful than others. And that's just to say that some people can do that work in less time than others, and that's what it means to be more powerful. So let's take a look at an example of climbing some stairs. So this time we've got ourselves a 60-kilogram Benny who is able to lift himself up a 4.5 meter staircase, and he was able to do it in 4 seconds. So we want to know, how powerful is this Benny? And we do know that Benny is in fact all powerful, but in order for us to consider this calculation, we're going to consider his lifting power. So in order to bring his 60 kilogram body from the bottom of the steps to the top of the steps, he is going to have to lift his mass or oppose gravity. So that means that his lifting force is equal to mg. And the only way that he can apply that lifting force is upward. Therefore, the amount of work that Benny is going to have to do to accomplish this is going to be equal to the change in potential energy that Benny will accomplish by lifting his body up that staircase. So we're going to say that in this case the work is going to be equal to mgh, where we're considering our reference point of 0 here and the 4.5 meter height here. So Benny's mass is 60 kilograms. He is applying that against the force of gravity. And he is lifting himself a height of 4.5 meters. And he's doing all of that in 4.0 seconds. So that means that his power output will be 60 times 9.8 times 4.5 divided by 4 seconds, or 660 watts of power. So that means that he did 660 joules of work every single second that he worked. So that means that overall he did 660 times 4 joules of work, but his average power was just 660 joules per second. And that was the power that he had to apply for the lifting. If we wanted to convert that into horsepower, then we would say 746 watts are in 1 horsepower. So it's actually going to be even less than 1 horsepower. So Benny is less powerful than a horse in this form. 660 divided by 746 equals about 0.88 or 0.9 horsepower. So Benny is almost as powerful as a horse in this situation. But this is his lifting power. Which means that we calculated his power to lift his body in this circumstance. So we only calculated the work that Benny did to lift his body, which means we only calculated his change in gravitational potential energy. But remember that when a person does something like climb up stairs, they do more than just lift themselves up. There's all sorts of things going on, and we receive that energy that we transform into the mechanical energy that we transform into gravitational potential energy from our food sources or our chemical potential energy. So that means that Benny and anyone else who climbs upstairs has to transform much more energy than just the 2,600 joules that it took to go up the stairs. We also had to transform chemical potential energy into potential energy for the brain to get it used and consumed from sugar. We had to sweat, and our body heated up in the transformation of energy, and so that means that some of our energy was transformed from chemical potential energy to thermal energy. So that means that it actually takes much greater amount of energy transformation than just the 2,600 joules of lifting power when a person climbs stairs, which is why you get hot when you work out. Every single time you have a change or transformation of chemical potential energy into other forms of energy, you have an extreme amount of heat generated, or thermal energy. And so that's why somebody can overheat when they're working out. So people aren't the only ones that can do work. Cars can also do work. Their engines are the ones doing the work. And most of the time, even if a car is going at a constant velocity, the car is having to do work, apply a force over a distance just to overcome friction. And when I say friction, I also mean air resistance. Because cars reach actual velocities where the amount of friction due to air resistance can be significant. A car also has to do work to climb hills. A car has to do work to accelerate in a forward direction. And all of that work comes from the force within the engine, and it all gets applied over the displacement of the car. And cars are limited to the rate at which they can do work. And most of the time, a car's ability to do work over time, or a car's power, is measured in horsepowers. And that's just because we're old school and we used to want to compare our cars to horses and be like, why would you want to buy that one horse when you can buy this car that can do 5 horsepowers of work? What? That's so much better. So cars, an engine's power is still measured in horsepower. When a car does work to overcome frictional forces or any other resistive forces, usually the resistive forces range in between 400 and 1,000 newtons. So that means that even if we were just considering the amount of power to overcome those resistive forces, we would still be looking at the engine's ability to do work over time. So power is work over time. Work is force times displacement, so that means that power equals force times displacement divided by time. If I factor this F out, then it's going to be force times distance divided by time. Distance divided by time, or displacement divided by time, is equal to velocity. So that means that we could calculate the power of an engine by multiplying the force that the engine can apply to the average velocity that it was traveling, which is really convenient for traveling vehicles like automobiles. So let's go ahead and let's take a look at some of the power needs of a car. We're going to be calculating the power required of a 1,400 kilogram car, and we're going to look at it as the car climbs up a 10-degree hill at 80 kilometers per hour. And we're also going to consider the power required for the car to accelerate along a level road from 90 to 110 kilometers an hour in 6 seconds to pass another car. For both of these cases, we're going to assume that the force of friction, or the resistive force that the engine must overcome, is 700 newtons. So, first scenario, a car going up a 10-degree hill. Well, we should probably sketch it out. Here's 10 degree, here's our car. That car is experiencing an mg. It's experiencing its applied force. It's experiencing a resistive force of friction. And it is experiencing normal force. If we break this down into components, we're going to get that the resistive force from the hill, right? mgx is going to be mg sine of 10, and mgy is going to be mg cosine of 10. Now, we're not really going to need mgy in this case because we're going to be able to assume the force of friction, so we're not going to need mgy to calculate the force of friction, which is kind of nice. But the one thing that we know is that in order for the car to move up the steady hill, its net force should be equal to 0. And that's going to come from its power, and it's going to be resisting the 700 newtons of friction and mg sine 10, the resistive in the x direction of gravity. So that means, and that would equal 0. So that means that the force that the car must put on, must use to move up a hill is going to be 700 newtons plus mg sine 10. We can get a numerical value for that because it's going to be 700 plus, and this is 1400 times 9.8 times sine 10, which is 0.174, and that's going to give us a total value of 3,100 newtons. So that's the amount of force that the engine must apply. So if we want to know the power, power is going to be equal to that force times the average velocity. Our velocity was given to us as 80 kilometers per hour. 80 kilometers per hour gets easily converted into 22 meters per second. And the force is getting applied up the hill. The velocity is in that same direction. So that means that we can apply the 3100 newtons times the 22 meters per second, and that would give us force times displacement over time, or 6.8 times 10 to the 4th watts. If I wanted to know what that was in horsepower, I'd have to divide it by 746 watts per horsepower, which would give us 91 horsepowers. So this engine's pretty much something. It's it can apply the power of 91 horses to get up that hill. And think about it, it's so much less of a cattle drive. So that's for going up a hill. What about accelerating? Well, if the car is accelerating on level ground, we've got its applied force, its frictional force, mg, and Fn, which are both perpendicular to the displacement. So that means that the net force in this case is going to be equal to Fp minus Ffr, and it's going to be equal to ma because the car is accelerating. So what we're going to need to do is we're going to actually need to calculate the acceleration in order to figure this out, because we don't know what Fp is. We do know that the force of friction is 700 newtons, and that's going to be times the mass, which is 1,400 kilograms. And the acceleration, well, we were given some variables. We were given 90 to 110 kilometers per hour in 6 seconds. So I can calculate acceleration from that. I'm going to convert 90 and 110 meters per second into 90 meters per second is 25 meters per second, and 110 meters per second is 30.6 meters per second. So 30.6 meters per second minus 25 meters per second. And that change in velocity happens over the course of 6 seconds. So our acceleration is actually equal to 0.93 meters per second squared. So I'm going to plug that in here, 0.93 meters per second squared. And now I have the resistive force, I have the actual acceleration and mass. I can use that to calculate the applied force of the engine, which in this case is, this is 1,400 times 0.93 is going to be equal to 1,300 newtons plus 700 newtons. So the applied force is 2,000 newtons. So interesting to say, it actually took more power to go up a hill than it did at a constant velocity than it did to accelerate at the rate which we accelerated. So now, power equals the force times the average velocity. So we're going to actually need to calculate the average velocity. The average velocity of those two is going to be 30.6 plus 25 divided by 2 times 6. But average velocity is all well and good, but what we're going to be interested in, or what is actually going to be more telling for us, is does the car have the horsepower to continue on at its maximum velocity that it was able to travel at? So the maximum power output to make this happen is given at 30.6 meters per second. So we're going to plug in for our average velocity 30.6 meters per second, and we get a maximum power output of 6.12 times 10 to the 4th watts, which if we divide that by 746 is 82 horsepowers, which, just like we assumed, is less than the power to go up a hill. So this is only the power of 82 horses instead of 91 horses. So most engines have a horsepower output of more than this. only about 60 to 80% of an engine's power output actually manages to reach the wheels, which is why even though your average car can make it up a hill like this, most engines have horsepowers of 100 to 150 or greater. So that means that even your like paltry, no big deal cars are still able to do these feats of acceleration and these feats of lifting with their paltry 100 to 150 horsepower engines. Which brings us to our last topic in power. Remember I said that only 60 to 80% of an engine's actual power output. So I'm not even talking about the total energy transformed, just the power output that it gets from its energy transformation. And that's how much reaches the wheels. But it turns out that only part of an energy output of a car engine reaches the wheels. Not only is some of the energy wasted getting from the engine to the wheels, but in the engine itself, a lot of the energy that's potential energy from gasoline ends up getting transformed into not very useful forms of energy like thermal energy. And you know that's true because, let's face it, you've touched a car after you've driven it, you know that the hood is warm, which means that the whole engine got hot. And so there's this calculation that we can do called efficiency, and it's the ratio of useful power output of the engine to the power input. And so the efficiency is the power output compared to the power input. And the efficiency will always be less than 1 because no engine can create energy. So that means that the fact that your engine is less efficient than 100% and cannot be more efficient than 100% is because of the law of conservation of energy. But under most circumstances, most engines are only about 15% efficient. And that's because of the massive amount of thermal energy that gets created or transformed from your chemical potential energy in the process of a running engine.